remember, I'm just giving you a big picture here. I'm not really giving you any examples yet. I'm going to give you a couple of examples in a minute. A hyperboloid of one sheet looks like a cooling tower on a nuclear reactor. So what would that look like? It would be something like you would expect, because it says hyperboloid, the oid is attached to the hyperbolo, that two types of traces will be hyperbolas, and one trace turns out to be an ellipse, one type of trace, that is. So in the traces, in a trace parallel with, say, the screen, the plane of the screen, you get these two. Well, they're two branches of the same hyperbola. And then if you took, say, the vertical plane that usually the way I would draw it, it would be the YZ plane. If you took that as your trace, so x equal, well, not the YZ plane, how about the XZ plane? You take y equals 0, then you'd get that guy as one branch of your hyperbolic trace, kind of coming out at you, and then this hyperbolic trace goes into the screen. So a hyperboloid of one sheet would have to have equation x squared divided by a squared plus y squared divided by b squared minus z squared over c squared equals 1. Whereas a hyperboloid of two sheets has two minuses in it. Its graph will have two branches. One branch kind of opens upward. It's kind of a bowl shape opening upward. And one branch is a bowl shape opening downward, like the reverse image of that bowl shape above. Again, I'm not giving you details yet. I'm just giving you the big picture, so don't stress. The origin would be right here in the middle. Over here on this one, by the way, the origin would be right there, kind of in the middle of the thing, too. And this guy would have equation something like z squared over c squared minus y, let's say x squared over b squared. Let's use a. A squared minus y squared over b squared equals 1. And without going into too much detail, so it has to look like this shape, because if you let x, y, or z be the appropriate trace, well, really the appropriate constant, you'll get one of these traces. So if you let, say, x equals 0, you'll get this hyperbola with the branch opening up, and then this branch would be the one opening down. So the main point here is you've got 6 quadric surfaces. This is all of them. And you need to learn to recognize their equations and draw a rudimentary picture just like I drew. If you need to throw in x, y, and z axes later on, do that. But it's easier to draw them first. So how do you tell, for instance, the difference between a hyperboloid of one sheet and a hyperboloid of two sheets? Well, look at the equations. How do you tell the difference? 2 minuses if it's a hyperboloid of two sheets and it satisfies the other criteria. It's got to have, you got to be able to manipulate it. There's other forms of the equations. These would be the standard forms, but you have to be able to manipulate it so that you get a 1 on one side, and then something squared minus something involving, it doesn't have to be z squared, one of the variables squared, and then minus on the other two variables, each individually being squared. So if you can write it that way, then it's got to be a hyperboloid of two sheets. Whereas for a hyperboloid of one sheet, it's just going to have 1 minus. All the variables are squared, but you have to be able to set it equal to 1 with the correct symbolic manipulation. Okay? So it takes some memorization, but there's only 6 of them. And so you're going to want to sit down and pretty much just kind of memorize this template sheet that I've given you. I know, no fun to memorize stuff, but these are the shapes we learn, the surfaces we learn calculus on. So it's really important that you know how to graph these, at least as well as me, and I'm not very good at it.